Okay, this is working.
Right. Okay, so we continue with another short talk by Eric Nilsson.
Yeah, thank you for the opportunity, and thanks to Peter for introducing the strange metal. So I don't have to do that. I'll be a bit brief, and this talk is about a recent paper together with Konrad, and you can see this as a bit of a teaser for Konrad's talk on Thursday, I believe. So what we're trying to understand in this paper is the following. So what happens to transport in a strongly interacting quantum critical metal that's placed in a periodic potential landscape? And in particular, when this periodic potential is strong. And I will explain this a bit further, but you can imagine naively strong translational symmetry breaking from this periodic potential. So this is what we want to study. And as a very brief teaser of what's about to come, so you don't fall asleep before lunch, I will try to show you that we get some sort of curved current flow through this potential landscape, which gives a roughly bilinear magnetoresistance, and possibly also the existence of a weak band metal to the like peak. But this is just to catch your attention. So let me take it from the top. So Peter introduced the weirdness of strange metals, and here's another weird fact about strange metals, and that's the magnetotransport. So we will consider just a piece of metal, you run a B field through it, and you can, in principle, then measure the longitudinal and the transverse conductivities. And if you do so, you find that the longitudinal resistance is roughly linear with the magnetic field for large fields, as shown here for BISCO and LSEO. And there might even seem to be the case that with this T-linear resistivity, it adds up on this square root quadrature form. So yeah, this is T-linear for when T is dominant and B-linear when B is large, as shown in this paper here. And this stands in quite stark contrast to the Fermi liquid type picture, which would be sort of B squared coming from a cyclotron frequency squared that would then saturate. So sort of similar to Fermi liquid is T squared, and here it's bilinear. So same type of story. So the setup for how we study this system, I'm going to be very brief here. So I'm just going to say we do this holographically, and maybe Aristos Donos will give a talk later about introduction to exactly next week.
Next Tuesday.
Next Tuesday. So it's just standard ADS4 Einstein-Maxwell for those of you that know this. But effectively, this will model a quantum critical in the large and limit strongly interacting system. And then the thing we add to this, to not make it like textbook holography, is to add this periodic potential that breaks the translational symmetry breaking. And we will talk about both 1D and 2D. So mu of x here is my spatially varying chemical potential, and formally this introduces an average chemical potential mu bar, a fluctuation delta mu, and then a lattice scale, if you like, lattice scale G, the space, And a comment for this is that when we do this, it introduces umklapp physics. So you get a copy of the folding of the Brillouin zone. This will come up later, but basically any physics at some momentum k, or in particular k equals 0, will be influenced by some scattering process that k plus minus g, so for reciprocal lattice vectors. This will appear later, but just so I've said it. Okay. Yes?
Holographic ignorance.
Yeah.
So even in the absence of this mu of x, do you already have a finite density system you're describing?
If you have mu bar, if you just have mu equals mu bar, it's finite density.
Okay. Yeah. So I guess the question is, are you? Oh, I see.
Yeah, you'll see on the next slide because that. So what we're doing here. So this system was actually studied by Andy back in the days, I think 2014, and in particular, if you take mu bar equals 0. So this is on average 0 density now. So take the rest of what I'm saying, you have to take with some grain of salt, but that's just to simplify this pretty complex problem. And then you get something like this in 1D. So the potential is something like this. And then why we want to do this is we want to look at the strong lattice regime, as I here will define as when the fluctuations are much larger than mu bar. And see Konrad's talk for a further motivation on why this is the case, but I think you will see, as I show the results, why you need these fluctuations to be large. So 2 warnings with this. There's some limitations. This means that the quantum critical system we're describing is this Z equals 1 relativistic quantum critical system. So ideally, we want to change this later, but just a note. And as a second consequence, we will not be able to study any sort of Hall physics because this transverse conductivity will be zero in this case. Boost away the B field, if you like. And there's also, there's zero average charge density. So these are definitely some limitations, but we're interested in general statements in this regime, which may still hold. And the outlook is, of course, to add this back in, of course. So this maybe is closer to something like graphene at charge neutrality, but that's a bold claim.
But this has propagating collective modes now, right?
Yes, you will sort of. So you will, yes, it has. There's some modes. So just to set the stage, what could we expect? If this is a strongly interacting system, it might be able to reach local equilibrium and thus have some hydro description. And then there is this old paper by Bless and Richard Davison. So this is homogeneous, the homogeneous case, relativistic hydro, although in the presence of some translational symmetry breaking scale gamma. So there's two things I want to say here. So here we have the conductivity, thermoelectric cross-conductivity and thermal conductivity. And formally, there's supposed to have this coherent Drude-like current with a peak. And this width is set by the momentum relaxation scale, which in our case would be proportional to the delta mu squared, so how large the fluctuations are. And then there's also this non-hydro or like incoherent contribution. Now, when we take the average chemical potential to be zero, you will end up in a situation where this guy vanishes. The electrical conductivity should be pretty much only incoherent and the thermal conductivity should be completely coherent. So it's not this simple, but just those are the expectations. So
no Franz Windemann law?
No.
Conventional.
No. So again, once we add this back in, the finite chemical potential, we will be able to get all these things. So first in one dimension, and this was done by Andy back in the days. So this is just to see what happens. So you know what changes once we go to 2 dimensions. So here I plot the conductivity as a function of temperature. And when I show the conductivity here, it's the average over one of these like periodic unit cells, if you like. And I'll focus here on the electrical conductivity sort of for briefness. The thermal will show up here. So the first thing, okay, so it decreases with temperature, perhaps as expected. But the funny thing is that it actually increases with stronger lattices. And this is perhaps, this is crazy from a Drude point of view because you're increasing the momentum relaxation rate, yet the conductivity increases. But this has to do with the fact that this is only this incoherent contribution. So it's a special case. And you could check, so it just becomes this value here. And there's an explanation in Andy's paper. It has to do with the anisotropy in the X and Y directions because you just have a 1D potential, but yada, yada. All I want to say is that there's a perturbative correction in delta mu squared here that actually increases it. But this is a model specific thing. But okay, this is how it looks like in 1D. Now I show you 2D. So I change the potential like as follows. And here's now the thing. The scaling with lattice amplitude is still the same. However, here we have something that at first looks weird. The conductivity increases with temperature. This is, of course, a far cry from a T-linear resistivity because it's something like T-inverse resistivity or something. So how can we understand this? So to do this, we looked at the spatially resolved currents. And for those of you that know holography, this is like the local Stokes equations on the black hole horizon, which govern the DC transport. So what I show here is this periodic potential in red and blue. So it goes from -44 here. And then the electrical current, I'm driving an E field to the right, and I'm computing the current vector. And large black arrows is large current. And then there's a much weaker current in these intermediate regions. And if you squint your eyes, you might be able to tell that the current is actually curving a little bit. So what seems to happen is that you have enhanced current flow in these potential pockets, which you could think of as hole-filled pockets or particle-filled pockets. And there you have more conductivity. And the current preferentially flows in these regions. So let's just now assume that these regions, you form some sort of local hydrodynamic description within these regions. So I'll take Bless's formula and I will just add some X dependence. Just bear with me. Now, yeah, this is, yeah, okay. So in these patches now, so say this patch, which is proportional to n squared, so it doesn't care about the sign of this chemical potential. Here, this guy will give me now a Drude peak. And the DC component of this is going to be much larger than the incoherent part. So this is a possible explanation then for this enhanced connectivity in these regions. So I'm going to claim that, okay, something like this is happening. To argue for this further, we looked here at, so here again, it's the conductivity as a function of temperature. And in the inset, it's the variance of the perpendicular current, Jy, that's going in the up and down direction here, as a function of temperature. So how much is the current allowed to move perpendicular to the applied electric field as I increase the temperature? And you can see that it basically has the same shape. So the more I heat the system up, the easier it is for the particles, constituents, to do something like this and flow in the regions where there's more conductivity, thus increasing the net thing. Yes.
Right. Can you explain why the conductivity is saturating at when temperature is bigger than?
That's a good question. No, I don't really know why it actually saturates.
Because in the absence of this
Yeah,
modulation,
it would just be one. Oh, there we go. It's just be flat.
it's not infinite.
No, because it's not Drude.
But maybe it's because I don't understand the model so well. But isn't the momentum?
Yeah,
certain
exactly. But because so I agree. If you remove the lattice completely, this guy is zero.
Yeah.
But if this n is zero overall, in that case, it's just a single n,
I see.
then this is still just set by this. So it's just a scaling argument. So it's a bit weird. Yeah, there are some quirks to this model, but
I see.
once you add back in a finite chemical potential, you get back conventional Drude physics. So this seems to indicate that the current can take some path of least resistance, and this evokes this effective medium theory type description. So what is effective medium theory? Well, you can imagine a piece of a material where you have different patches of different conductivities. So if you now cook up some microscopic models for each of these small patches, like Sashka paper from 2018, and then you just like, okay, you say that there are some mesoscopic patches that have slightly different parameters and thus slightly different conductivities. Once you then drive a B field through this perpendicular, as the current now travels in a curved path, it will pick up a contribution from the Lorentz force every time it turns. And that will in turn influence the magnetotransport, non-trivial. So what they showed in this paper was that you will actually end up with this sort of this quadrature, square root quadrature type form for the longitudinal resistivity, and in particular, a bilinear resistivity. But this is something you add, at the end to the model. You say, oh, this is my microscopic theory, and then I add these patches. So what happens for us? Because if we believe that we have this description, it just appears naturally for high temperatures. So here is our longitudinal magnetoresistance. The insets for 3 temperatures that are sort of in this regime where we have this increased conductivity, so where the current is allowed to flow like this. The insets shows the resistivity, which is roughly linear. And then the main panels is the logarithmic derivative. So at least for the higher temperatures, let's see, here is 1. So there's this maybe like 2 decades where it's roughly 1, 1.3 to 0.9 or something like this. So indeed, this seems to be the case, just pops out naturally in our model for large temperatures in these units. And then to answer Peter's question, I will just briefly mention also AC transport. So again, this is a bit peculiar because of this zero average chemical potential, and I don't want to digress too much, but what you have in the 1D case, here's the optical conductivity and the thermal frequency dependent conductivity. Then it turns out that the optical conductivity is dominated by this umklapp copy of the sound mode. That's why I mentioned umklapp before. So that's what this peak is. It's not really important for the message right now. And for completeness, I will say that the peak in the thermal sector is actually a Drude, the Drude peak, Drude mode, and an umklapp sound that collides and turns into a propagating mode. And this turns out to govern the thermal sector. But
Umklapp sound means there's a mode at finite Q that's folded back to Q equals 0.
Exactly. So that's why this dashed line is exactly the speed of sound if it was perfectly conformal.
Okay.
And then it renormalizes weakly because I'm not at this normalization. But now once I go to 2D, what happens? So I still have this umklapp sound peak, but there's also a broad peak at small frequencies. And it's a bit harder to see for the thermal one, but it's basically the same story. This normal peak from before has this additional Drude-like peak, broad type peak at 0 frequency. And this increase here is precisely what gives me the increase in the DC conductivity that I saw. So again, if I allude to this picture, how can I think of this? Well, here's the electrical conductivity. I have an E field to the right and I look at the current. In each of these regions, if you believe me, you assume you have some local hydro description. Each of these guys contributes a Drude pole. And because I have more net current flow in these regions than in the intermediate regions, when I average, they still end up with some sort of residual Drude pole that sort of survives the averaging. Note that in one dimension, this is not the case, because if I have a 1D potential that's like valleys, it will just completely cancel out because you can't flow more in one region from another. The thermal is the same, but a bit opposite. So here you actually see that you have more thermal flow in these intermediate regions, which you can understand from this Drude weight actually being the largest when this guy is 0, because then it's just S squared T over ST, so it just cancels. So it's more or less the same thing. If you have more flow in these regions, you have a stronger type Drude peak that upon averaging leads to this weak extra thing. And in case you're wondering, the insets just show that these two peaks are not the same mode, they're different modes because they scale differently. But so it's like an emergent phenomena in both the electrical sector and the thermal sector. And with that, we're all hungry for lunch. So I'm going to wrap up and say that we studied a strongly correlated quantum particle system in the regime of large lattice fluctuations, let's say. And we seem to get, at large-ish temperatures, an effective medium theory-like description of the system. And with that, a roughly bilinear magnetoresistance and the appearance of this extra Drude-like. A curious fact about this is that this regime seems to happen for large temperatures in my units. So what does this mean? If you think of this periodic potential as the lattice, like the actual lattice, so let's say G is 2 pi over A, then this temperature to have T over G equals 1 would be something like 10 to the 4 Kelvin. So that's not it, right? And then you would have to have collectivization on a tiny scale. If you flip the argument and you say, okay, I want this thing at like 100 Kelvin room temperature, and I assume like Fermi velocity is typical 10 to the 5 or something like this. What's the length scale that would correspond to give me this? Well, it's something like 500 nanometers. So again, evoking this picture of like you have a piece of material that has these regions, patchy regions, and each region is big enough to give you some local hydro. And then once you average over the entire thing, you get these signatures. And I have a vague memory of Peter saying something about some jamming or some structure. I believe that was a lot smaller than 500, but like a structured liquid. But yeah, that's a separate thing. So of course, the future here would be to add back in a finite chemical potential and get back some of the physics that Ian was asking about. This will also give us, in the IR at least, local quantum criticality, C equals infinity. And there are holographic realizations of local quantum critical systems that also give T linear resistivity. So then the question is, once you combine these two things, do you get the square root T squared plus B squared that is both T linear and B linear at large T and B? And in that setting, we will also be able to study the Hall angle And those of you that know that this is also anomalous, or I guess not anomalous in strange metals, because that's a different scaling from the longitudinal resistivity. And this is a wild guess, but potentially this extra time scale that corresponds to this emergent Judah peak, that gives you another time scale. So maybe there's some connection there that we'd like to explore further if it actually changes this as opposed to sigma XX. And with that, I thank you for listening, and I'm happy to take questions. Yeah.
Probably I just missed it, but how important is it that the potential you've added is actually periodic? I mean, what if I just added some,
Random?
Yeah, just a random.
Yeah, so there was a paper recently that looked at the SYK type, like completely random, like averaging over multiple, super high frequency versions.
Yeah.
That was at finite mu, though, like finite average potential. But there was, let me see if I remember, there was one of the DC plots were actually quite similar. Maybe, I think, yeah, so then in that case, they were at finite chemical potential. So then, of course, you get they flip like this. So more translational symmetry breaking dampens the conductivity as it should be, because you have Judah physics. But I believe they had a similar curve like this. That's all I can say about that. But that was sort of randomly averaged. Yeah.
Just on it's probably not so related, but there is also from Brian Skinner's group some hydrodynamics through disordered landscape. There's some percolation.
I see.
Eric, not being in holography,
Yeah.
it's not super obvious to me why the non-zero chemical potential is such a problem to do.
No, it's from the point of view here, it's just I can do it. I think I'll have some preliminary results for Kunal's talk on Thursday. But it's basically reducing the parameter space, right? Because I introduced 3 parameters, mu bar, delta mu, and G. And if I set mu bar to 0, that's just 2 left.
Okay, sure.
So it's simpler. But I can add it back in. And then there's a minor comment on the fact that the numerics can get a little bit trickier, but it's not a big issue once. But if you want T over mu very small, T over mu bar very small, the geometry changes a bit, so it's a bit nastier, but it's completely doable.
Okay, yeah, because it seems like in your sort of picture of being kind of at charge neutrality and kind of having your chemical potential take you between the electron and hole
exactly
sectors, that at finite chemical potential, you could imagine a case where your delta mu kind of keeps you within, say, just your conduction.
Exactly, and that's one of these points for having the strong limit, right? Because if you just have some average and it's just weakly fluctuating like this, that has been done, and this just gives you sort of what you expect. It's like sort of hydro with umklapp from these modes. But what you want is something like where this is still large, but maybe now the average is here or something.
Sure.
Because this is the strong translational symmetry breaking regime in this context. Sorry.
No. Last question maybe. So it's about the temperature dependence of the conductivity, which is very unusual.
Yes.
Have you measured other things like say the shear viscosity?
That would be a different. Yes, I could. I guess that's just a different correlator. I could.
The reason I ask is because I remember there was some general hydrodynamic, at least in weakly disordered electronic systems.
Yep.
There were some, I think, general relations in the hydrodynamic regime between the conductivity and the shear viscosity.
Yes.
And so I'd be curious if, because the temperature dependence that you showed for the conductivity is one that you might expect actually for the viscosity.
Yes, right. It's like when you get this, you actually get like sort of the Gaussian, like this dip, right?
Exactly.
Yep. That's actually interesting. We could look at that. Yes, but I can tell you, as soon as I add back in a small finite mu bar, this curve flips, so you get like you get a decrease in the conductivity with increased mu bar very quickly.
I see. So do you think there's any chance of getting something non-monotonic or?
Yeah. Can I? Do I share my entire screen or just this right now? Let me be very brief, so not to stop sharing. There. Entire screen. Non-monotonic. Is this?
Getting the mathematical code out.
Is this non-monotonic? This is a bit janky, but this yellow curve is very non-monotonic to me, I think.
But
This is
I'm not
the
sure.
variance. Something like this.
You made an algebra mistake.
Yeah, this one, this one. This yellow one. This is the conductivity now for some finite new one.
Conductivity.
So this is very non-monotonic. It does like
Yeah.
something like this.
And what are the colors? Oh, that's
This is the
delta.
lattice amplitude. So yellow is strong lattice amplitude here. Same as before.
Yeah, that's quite interesting. I mean, you see, well, usually it's plotted as the resistivity, but in some, strongly correlated electron gases,
Yeah.
you have a non-monotonic
Yeah.
resistivity, and people.
So basically in this region, it behaves like before, I think the paper I looked at, but then the sort of finite average chemical density takes over in this regime, I think. So you get this in, that's why it flips. I remember. Yeah, okay, let's not show.
Okay, cool. Thanks a lot.
Okay, if there are no further questions, let's thank Eric again.